In this video, we are taking a very quick look at the idea of images and inverse images when dealing with functions. So suppose we have a function and it's defined from a domain A to a codomain B. So let's say this is our domain A, function acts on it, and then we have our codomain B over here. What would happen if we restricted the domain? So if we only looked at a subset of the domain, namely some C, we would like to know what is the image of C. So what does FC represent? So the definition of what this is really just f of C would be all function values. So all f of x, where x is restricted only to C, not perhaps the full domain A. C could be a proper subset of A, but it could also be equal to the set A as well. So here, C could be any subset of A. What is the inverse image? Well, this is if, again, we have a function, let's say from the domain A to the codomain B. And here we take a look at a subset of B. So let's say, for instance, we choose a subset here and call it D. And again, D could be a proper subset of B, or it could be B itself. The idea is we want to see which elements in A are mapping towards D. And this is what we call the inverse image of D, or F inverse of D. And how we define this, F inverse of D is simply going to be all elements in the domain such that when we apply f of x to these elements, the result gives us an element in the set D. Here is our first example. We have a function from R to R defined by y is equal to x squared minus 4x. It's a parabola, it's upward facing, but it has been translated. If C is the interval from 0 to 4, endpoints included, what is the image f of C? One of the best ways to find images, if we can sketch the graph, is to restrict the domain on the image or on the graph itself and to see how does it affect the range of y values. So let's do that. Let's do a quick sketch of our graph. If we have that y is equal to x squared minus 4x, we can set y equal to 0 just to find our x-intercepts. So common factor, if we remove an x, we get x. What's left will be x minus 4. And so x is either equal to 0 or x is equal to 4. If we do a quick sketch of our graph, it cuts the x-axis at 0 and at 4. It's an upward facing parabola, so it's doing something like this. The turning point will be right in the middle of the two x-intercepts, so this will be at x is equal to 2. And then we can just determine if x is equal to 2, what is the height of the function? Well, if x is equal to 2, then y will be 4 minus 8. So this will be at height minus 4. All right, let's restrict our domain. We are restricting the domain to this interval. X falls only between 0 and 4, 0 and 4 included. So on the graph, we are only looking at these x values from 0 up to and including 4. And our question is, if we are only restricted to these values, which y values are we getting out? Now, if x is equal to 0, our y value is equal to 0 as well because it's an intercept. But as we move through this interval, we have the following y values. Our y values keep decreasing up to where x is equal to 2. We reach a y value of negative 4. But then the y values start increasing again up to where we find our second x-intercept, which is at x is equal to 4. This is where y is 0 again. So for this restricted part of the graph, our y values span from 0, from negative 4 up to 0. So this is our image. This is the effect on the graph or on the function values if we restrict x to that particular interval. So f of c will be the interval from negative 4 to 0. Here's our next example. We have a function from the interval negative 1 to 1, endpoints included, to r, defined by y is the positive square root of 1 minus x squared. Our restricted domain, or our subset C, is the interval from 0 to 1 only, including endpoints, and we want to see how this affects the y values. So again, let's do a quick sketch of our graph. If we take the equation and we square both sides, we get y squared is equal to 1 minus x squared. And this is true if and only if we take the x squared over to the left, and we get x squared plus y squared is equal to 1. So we are dealing with a circle centered at the origin. Easy enough. Radius 1. But we do have a restriction. Originally, we said y is the positive square root of 1 minus x squared, meaning y is not negative. This means we exclude that lower half of the circle. We are only looking at the upper semicircle, radius 1. Now, you can see the domain here is from negative 1 up to 1, endpoints included. We are now restricting the domain to the interval from 0 to 1. So we are saying x is anything from 0 up to and including 1. How does this affect the range? How does it affect the y values that we get if we only use x values from this interval? Well, if x is equal to 0, it takes us all the way up to where y is equal to 1. But all the other x values, if x increases from 0, our y value starts decreasing up to where we reach x is equal to 1, which is an x-intercept, and so our y value there will be 0. So the y values that are covered here means we are working from a height of 0 up to and including a height of 1. This is our image f of c. Which is in fact also the range of the function. So in this case, restricting the domain to the interval from 0 to 1 has no effect on the range. For our third example, let's take a look at the inverse image. So in this case, we have a set D. It's a subset of our codomain. It is the singleton containing the element 0. We want to find the inverse image of D. What exactly does it mean? Well, F inverse of D, or F inverse in this case of the singleton 0, will be all of the x's in our domain. So all of the real numbers that satisfy the following condition. F of x must be an element of D. Now D only has one element. D has only the element 0. So we can rewrite this to say we are looking for all elements in the domain such that if we evaluate f for those elements, now f of x is defined to be cos of x. So here we can replace f with cos. Cos of x must be an element of D. The only element is 0, so it means cos of x must be equal to 0, which is something we can easily solve. We can take a look at the graph if it helps a little bit. There's our cos graph. It cuts the x-axis here at pi over 2, and again at 3 pi over 2, and continues in this pattern. We are looking for the x values where cos of x is equal to 0. So here, the first one that we encounter is x is pi over 2. But you can see this repeats. Even if the graph continues here on the left, it will be at negative pi over 2, again at negative 3 pi over 2, and so on. It's not really to scale. This repeats every pi radians. So here we can say x is pi over 2, and in general we can add a plus k pi. This covers all of the extra x values where cos of x will be 0. So k is any integer. So this is the set that we are looking at. We are looking at all pi over 2 plus k pi, where k is an integer. For our last example, we again want to find the inverse image of some set D. We have a function f of x is equal to ln x, and we want to see if the y values that we get out are from negative infinity to 0 excluded, meaning we only get negative y values, which x values will give us this result. So if we write out formally f inverse of D, what are we looking for? We are looking for all of the elements in the domain. In this case, x must be an element of R plus. X must be positive for ln to exist, such that f of x results in an element in D, meaning f of x, the y value must be negative. So I'm going to expand on this all the way. We are looking for x in R plus. F of x we know is ln of x. If it's an element of D, D is from negative infinity to 0. So ln of x must be less than 0. This is what we are looking for. And even if we don't know what the graph looks like, this is a pretty well-known standard one, so we can also read it from the graph. We'll do that in just a moment. But we can take this inequality, solve it for x. We can take e to the ln x on the left, and on the right the same thing, e to the 0. What is this going to give us? Positive x, such that on the left-hand side, e and ln are inverse functions. So this gives us x must be strictly less than e to the 0, which is 1. Now we can describe this in terms of an interval if we like. X is not just less than 1, it must be in R plus, meaning it must be positive. So x is from 0 excluded up to 1 excluded. This is our inverse image of D. If we wanted to read it from the graph, this is what we would do. This is how we would do it. We would sketch our normal graph. Y is equal to ln of x. We know this cuts the x-axis at 1. We want to see if our y values are negative. Where are the y values negative? This part here on the graph is the part that lies below the x-axis. So we really just want to see which x values will give us these y values. So if we take these y values and retrace our steps back to their inputs, you will see that these y values are from 0 or between 0 and 1, 1 excluded. So here, if x lies within this interval, then it will imply that f of x will always be negative. And this is exactly what we were looking for.